Hi everyone, today we are going to talk about the trigonometric form of a complex number. So the trigonometric form of a complex number can be really useful for various things, including multiplying and dividing complex numbers or working with powers and roots. So the first thing we're going to talk about is how to write a complex number in trigonometric form. So it's always going to be this nice formula, r times the cosine of theta plus I sine of theta. So really you only have to find two things. You have to find r, which is just the modulus of z. So essentially it's just the square root of a squared plus b squared, which we talked about in a previous lesson. And then you just have to find theta. And you can find theta by setting up a simple trig ratio using tangent. So tangent of theta is b over a. Now I just want to talk for a second about where all of this comes from. So remember, we're working with some imaginary number a plus bi. So let's say that it is right here. So a plus bi, so this would be the coordinate AB in the complex plane. So really what's happening is we can always form a right triangle where this leg is A and this leg is B. Now if we're trying to find the hypotenuse of our right triangle, we would use the Pythagorean theorem, and it would end up being square root of a squared plus b squared, which is just our r value, which is our modulus. So that's where this comes from right here. So it's really just the Pythagorean theorem finding the hypotenuse of your right triangle. And then where does this come from? Well, if we want to find what theta is, and we know what the two legs are, we would set up a ratio using opposite, which is b, over adjacent, which is our a value. And then these two things right here, I want to talk about these really quick. Where do these come from? So we can actually make two different equations with our information. We can say that the cosine of theta is a over r, which is our hypotenuse. So a is just r cosine of theta. And we could also say that the sine of theta is b over r. So b is r sine theta. So you might see your trig form written out like this, or you might also see that r value distributed in. It's very common to see it look like this: r cosine of theta plus r I sine theta, something like that. So sometimes you'll see the r distributed out, or sometimes you'll see it out front. But either way, it's really just coming from a simple right triangle, and all you have to find is your r value and theta. So let's practice doing this. We're going to write negative 2 minus 2 root 3i in trigonometric form. So for this problem, our a value is going to be negative 2, and our b value is negative 2 root 3. So the first thing we're going to need to do is find our modulus. So we're going to take the square root of a squared plus b squared. So this ends up becoming the square root of 16, which will be 4. So that's our modulus. And now we need to find theta. So we're going to set up a ratio with tangent. So tangent of theta is going to be b over a. So we need to figure out when the tangent of theta is positive root 3. However, you also have to keep in mind what quadrant we're working in. Here we have the complex number negative 2 root 3i. So that's going to be some coordinate down here. So we need to find some angle that is in quadrant 3. So our reference angle is going to be pi over 3, because the tangent of pi over 3 is root 3. But placing that into quadrant 3, we get 4 pi over 3. So now we have theta and we have r, so we can write it in trigonometric form. So z equals 4 times the cosine of 4 pi over 3 plus I sine of 4 pi over 3. And that's all there is to it. So make sure you have a really thorough understanding of this, because writing something in trigonometric form is really just going to be the first step of a larger problem. All right, so why don't you go ahead and pause the video and give this problem a try. All right, go ahead and check your work here. you should end up with 6 root 2 times the cosine of 7 pi over 4 plus I sine of 7 pi over 4. Okay, now we're going to try doing the exact opposite. We're going to take something that is in trigonometric form and we're going to write it in standard form. So the first thing that we're going to do is we're actually just going to simplify our trig values. So, oops, let me switch back to black. So we have square root of 8, which I'm just going to simplify to 2 root 2 times, so the cosine of negative pi over 3 is going to be positive 1/2 because it's a 60-degree reference angle in quadrant 4. And then sine of negative pi over 3 is negative root 3 over 2. So I'm going to say actually minus root 3 over 2I. And now all we need to do is distribute in our modulus. So z is going to be root 2 minus root 6I, or we could say I root 6, just so it's really clear that the I is not under your radical sign. Okay, so go ahead and pause the video and give this problem a try. See if you can write this in standard form. Okay, so if you simplify, you should end up with negative 4 plus 4 root 3I. All right, so now we're going to talk about why we like to keep things in trigonometric form or put them in trigonometric form. So one reason why is because it can actually make multiplying or dividing complex numbers pretty quick and easy. So I know these formulas look scary, but before you get intimidated, let's just see what's happening. So if you have two complex numbers that are already in trigonometric form, you can find the product of those two complex numbers by simply following this formula. Multiply your R values and then add up your angles. And then all you have to do is simplify. So it's really straightforward. Multiply your R's, add up your thetas. Now if you want to find the product of those two complex numbers, it's very similar, except now you divide your R values and you subtract your angles. And then once again, all you have to do is simplify. So these look like really scary formulas, but really you're just going to multiply and add or divide and subtract. So let's give this first problem a try. So here we're going to be multiplying two complex numbers. So to find the product of z1 and z2, first we multiply our R values. So we have 3 times 2, which is 6. And then all we have to do is add up our angles. So we're going to find the cosine of pi over 4 plus 3 pi over 4. And then I sine of the same thing, pi over 4 plus 3 pi over 4. And now we just have to simplify. So we will have the cosine of pi plus I sine of pi. So we have 6 times negative 1 plus 0. So the product of those two complex numbers is simply negative 6. So remember, multiply your R's and then add up your angles and then just simplify from there. All right, so now let's try doing a quotient. So we have the quotient of two complex numbers already written in trigonometric form. So remember, the way you find the quotient is by dividing your R values. So we're going to do 24 divided by 8. So 3, and then we are going to subtract our angles. And this might be something that you can do in your head, but just want to show out all of the steps for now. So we have 3 times the cosine of 225 degrees plus I sine of 225. So this is just going to be 45 degrees in quadrant 3. So they're both going to be negative. Minus. And then from here, all we have to do is distribute in our 3. So we are left with negative 3 root 2 over 2 minus 3 root 2 over 2i. And that's all there is to it. So remember, when you are finding the quotient, divide your r values and subtract your angles. And then you're just simplifying. All right, so let's try a couple examples. Go ahead and pause the video and try to find the product of z1 and z2. Okay, go ahead and check your work here. You should end up with just 10. All right, here's another example. Go ahead and pause the video and give this a try. You're finding the product again. All right, go ahead and check your answer here. And notice when I had cosine of 5 pi over 2, I just rewrote it as cosine of pi over 2 because they're coterminal angles, so they're completely equivalent. So I just did that to make it a little easier to simplify. All right, last example for this type of problem. This one, be careful, is a quotient. Pause the video and give it a try. All right, check your work here. Your r values are both just 1, so you should end up with root 3 over 2 plus 1/2 I. Okay, so another reason, and this is really an actually pretty important one, that we like to put things into trigonometric form is because it makes it way, way, way easier to raise a complex number to a power. So just to put it into some perspective, like imagine you had negative 5 plus 2i to the power of 8. This would take you a really long time to multiply out, and it'd be very easy to make a small mistake. So luckily we have Moi Theorem, which looks scary again, but really if you look at it, you're raising a complex number to the power of n. All you have to do is raise r to the power of n and then multiply theta by n, and then you just simplify. So once again, you're raising r to the power of n and you're multiplying your angles by n, and then you simplify from there. So this can save you a ton of time. Whenever you see a complex number raised to a power, convert it to trig form and then use this theorem. Okay, so let's give this example a try. So here we have negative 1 plus root 3i to the power of 12. So the first thing we need to do is we need to write this in trigonometric form. So our a value is negative 1, our b value is root 3. So let's start by finding our modulus. And this is what I'm talking about, that converting is just going to be a small part of a bigger problem. So this is going to end up being root 4, which is 2. So that's our r value. Now let's find theta. So tangent of theta is root 3 over negative 1. I know that we are working in quadrant 2, so theta is going to be 2 pi over 3. And of course, if it helps, you can always kind of plot out your point. Negative 1 root 3 in the complex plane would be somewhere up here. So that might help you to determine what your angle is going to be. So we have r and we have theta. Now we can write this as in trigonometric form. So z is going to be 2 times the cosine of 2 pi over 3 plus I sine of 2 pi over 3. So now if we want to find z to the power of 12, let's use Moi Theorem. So we're going to raise r to the power of 12, and then I'll put this in brackets. We're just going to multiply our angles by 12. I'll say 12 over 1. Plus I sine of 2 pi over 3 times 12. From here, so once again, this is what we did. This and this. So from here, all we need to do is simplify. So z to the power of 12 is 4,096, that's 2 to the power of 12, times the cosine, so this is going to end up being 8 pi. And just to make this a little bit easier to simplify, I'm going to rewrite this with a smaller coterminal angle, and in fact, a coterminal angle to 8 pi is just 0. And now we just have to finish simplifying. So cosine of 0 is 1, sine of 0 is 0. So z to the power of 12 is just 4,096. So this is certainly something where using this theorem can save you a ton of time. It will help you avoid small mistakes, and it's just much, much easier. So if you ever see a complex number raised to a power, write it in trig form and use Moi's theorem. Oops, sorry about that. Go ahead and pause the video and give this answer a try. You just saw the answer already, but I'll show you in just a few seconds. Alrighty, so first check that you have correctly written it in trigonometric form. The trigonometric form should be root 2 times the cosine of 5 pi over 4 plus I sine of 5 pi over 4. And then to the right, you can see that we used Moi's theorem, and you should end up with -4. All right, the last thing we're going to talk about is something that's a little bit more complex, but it can be useful. It is a little bit tedious as well, and it's finding the nth roots of a complex number. So essentially what's happening here is if you want to find, like, let's say you want to find the 6th root of some number, you can expect to find 6 answers. So first you're going to use, this is kind of our setup. This is our formula. So you take the nth root, so we would take the 6th root of our modulus, r, and then we set up this same formula every time. We say the cosine of theta plus 2 pi k, which we'll talk about in a second, over n, which would be 6 if it's the 6th root, plus I sine theta plus 2 pi k over n. So this k value represents the integers that you're going to plug in to find your different answers. So notice that you're going to start at 0 and you plug in the next whole numbers up until 1 before your n value. So for example, if you're finding the 6th root, you'll plug in 0, 1, 2, 3, 4, 5. You stop at 1 before your root. So let's give one of these a try. Sorry about that again. If you want to find all of the 6th roots of 1, you can actually use this, even though technically it's not a complex number. We can still write it as a complex number. So first we need to write it in trigonometric form. So here, our a value would be 1, and our b value would be 0. So to find our modulus, we would just do the square root of a squared plus b squared. So our modulus is 1. And then we can still find theta. Tangent of theta is b over a. So theta is just 0. So 1 in trigonometric form is just 1 times the cosine of 0 plus I sine of 0. So now we're going to set up that formula that we just used. So to find the 6th root of z, we're going to take the 6th root of 1, and let me turn that into a bracket. We are going to plug in some k values to the cosine of 0 plus 2 pi k over 6, which is n, plus I sine 0, which is our theta, plus 2 pi k over 6. So this right here is our formula. And then what we're going to need to do is we're going to need to plug in some k values. So since we're finding the 6th root, we're actually going to substitute the k values 0, 1, 2, 3, 4, and 5. So we end up with 6 distinct answers. So here I've already written out the work for this. So it is a little bit tedious. You do just need to go through and substitute all 6 of those k values, and you get your 6 roots. So you have 2 real roots, +1 and -1, and then you have 4 imaginary roots. So it is, like I said, a little bit tedious, but it will work. Now you can also do this for imaginary numbers. So let's say we want to find the 3 cube roots of this imaginary number. So first, once again, we're going to write this as in trigonometric form. So our a value is -2. And our b value is positive 2. So let's find the modulus. So our r value is going to be the square root of 8. And let's find theta. Tangent of theta is b over a. So I can see here that theta must be 135 degrees, or we could say 3 pi over 4. And actually for this problem, let's just use degrees. Let's give it a try. Okay, so that means that the trigonometric form of our number is going to be root 8 times the cosine of 135 plus I sine of 135. So now we're going to set up our formula using that nth root equation that we just talked about. I'm going to zoom out just a little bit. And it ends up looking like this. So to find the cube root of z, we're going to take the cube root of our r value, so it actually becomes the 6th root of 8. So the cube root of the square root of 8 is the 6th root of 8. And then we're going to do cosine of theta plus 2 pi, or 360 since we're in degrees, k over n, which is 3, plus I sine, let me put little degrees there, of 135, which is theta, plus 360 degrees k over 3. And just remember, our formula that we talked about earlier was in radians, so it said 2 pi k, so I just used 360k. And now, since we're finding the cube root, we're going to plug in the values 0, 1, and 2. So remember, we always stop 1 before our n value. So once again, we're just going to substitute our k values here to get 3 distinct answers. And you should get something that looks like this. So here, you actually have 3 complex answers, and you can see that some of them you would have to use a calculator to get a decimal approximation for. So like I said, this is definitely a tedious process, but it will work. You're just kind of setting up the formula and then plugging in values and going from there. Okay, that is all for today. Thank you for watching.